systems will be a very valuable addition and something where you get a lot of information out of it. So the lecture will be what is a GIS, what is spatial data, and how it is represented in a GIS, and then we look at some applications, how we can actually take advantage of that. So maybe as an introduction to that, like 15 years or 20 years ago, it was already impossible to get any of kind of geospatial information. Usually you would have to go to some local authorities and apply for some data, and then you got a printed map. So usually if you're not on the authority agency side, you had no access actually to this digital data. You just got something. Maybe if you were lucky, you got a CD with a DXF file format there. And today, with Google Maps and everything else, there's even public available GIS data. And there are even open source possibilities to get geo information from all over the world. So there's, of course, always a kind of trade-off between quality, but usually there is a kind of vast base of information what you already can get without paying anything. That's really important if you start just your businesses and so on, architecture. So maybe just beforehand, and it's like a little kind of comparison between even like what are the most familiar data types that you're using, maybe like pixel data and vector data. So there's already like a first kind of value here put inside here. Pure data is without context. So it has without actually, you just know the context, then it becomes information. But it's not attribute, it's not inside. But to make it available to more people, for instance, to just have a drawing of a house, a hand sketch, and only the people that know how to read your sketch will find out, yes, this is a house, so this has the information. So it is very important that data is transformed into information. And yeah, basically, even from this information, you can make queries and you can request something and you can even automate this kind of processes. So that makes sense to transform data that you have to acquire, that you have been working on, and track this and put this into an information system so that you can later make a query and get, again, this meaningful information. So, and what is an information system for? Yes, it's a system used for capturing, storing, manipulating, updating, and analyzing data. So, and how can it look like? Usually you have something like a database where everything is stored. It can be just a simple file. It can be like a very specialized, overwhelming system on a server. It can be your mail application, which has as well a database. And usually, besides the storage of the data, there's something, a component of the software, which takes all the kind of queries and all the kind of things to get this data here and there and store it and change it and so on. And everything is based on your particular request, what you want actually to get out of the system. I think this is a very common information system, just a simple front end of a shopping system, very familiar with, I think you are. And this can be very complex, and even certain things of data mining, like doing associative rules, if you got this kind of suggestion for your next shoppings and so on. These kind of things are just implied because you have this huge data set and you have a certain behavior of the user inside. And this wouldn't be possible with raw data, actually. So if you combine such kind of a database, not just with books, maybe with shapes, together with a clarified geographic position, you can retrieve spatial data. And you can put in there spatial data, you can change, and you can do analytic processes on this one. So the idea is of a GIS system, a geographic information system, that you can link graphical features to tabular data entries. So these are like sheets that you have, and this sheet is maybe connected to this point here. As there's a single point, And there is a kind of report what you get out of it, and there you got the list. This is the difference between a DXF or just a raw CAD drawing. There you just have a shape with a hatch inside. And maybe you can query the area of the hatch, but that's all. And at a certain point here in a GIS, you can have could be a composed function of different kind of layers that just recreate this layer here just by calculation, for instance. So here, for instance, is an example. What are the biggest companies here in Manhattan? And what would that actually mean if you have a company here with a size of 1,000 to 90,000 placed here? What does this mean for traffic, for infrastructure needs, and so on, and even for tax income? So a GIS system is a system, hardware, and database engine that is designed to efficiently assemble, store, update, analyze, and manipulate and display geographical referenced information. So, and actually, if you see here, it's pretty much next to the design process. At the beginning, we want to find out about a problem. We find out the criteria for the GIS. We build a data set because we want to do something there, like all our maps together, for instance, and connect it with statistical information, for instance. And then we do an analysis. What are the areas with the biggest income? Where is the area with the highest segregation? And sorts of things. And so, for instance, in urban planning, you could find out, oh, this might be, or this may be later on problematic spaces, places in my city. And I should shift a bit of my development policies to counteract on that. Then you get an output of this analysis, and then you can make a decision or go a next round again. So these are the basic steps. And I think it is actually pretty much similar to what we are doing more intuitively in CAD system or building information modeling systems. But still, if it comes to urban design and urban planning, we are mainly just using raw geographic, not really geographic, just drawings. And that's a bit of pity at the end. So I think this section here, this graphics explains it quite well, what a GIS system is and what kind of data types we have inside. So this is maybe a picture of the real world. So we have like geo information for soil and so on. Then we have maybe here some nature reserved areas. And we have something urban, we have waterways, we have traffic ways. And this can be translated in like this portions here. For instance, in raster information, what you can have here, for instance, just everything will be translated in the grid. Next step would be possibly that you want to have, as a raster information, as an elevation map, you want to have all those heights here. Then you can come to the more or less vector level, since there's the granularity of the resolution is just too low for raster. And we come then to parcels, streets, and maybe point informations. This could be single households or whatever, customers in this case. And to each of this kind of thing, you have always like to this certain point here. You can query a table of information. A table with an object identifier, so every little information here has an object ID. It's automatically created usually by the system. You can reformat it if you want. And like certain kind of background information, like date sampled, concentration, whatever. And here, for instance, what are the typical companies here, like postal addresses, population size, how many people are living in the Circuit Street or on the Plain Street, Webster Street, and so on. You can really query it, and then you get, next to the more real-world picture, you get like the quantitative analysis of what's happening inside this place. So maybe back to raster. So that's a raster. You have a grid here. This is all what you actually know from JPEGs, PNGs, and BMPs, whatever, TIFFs. The thing is that this cell here is not just a stupid pixel, it's actually a stupid pixel, but with a coordinate attached to it. And this makes it a bit different. And sometimes you even have certain dynamic ranges. Usually, usually you have per color channel like 265, 65, yeah, near 56, yeah, kind of steps per pixel. Here you have usually higher, like 16-bit and more resolution. So, yeah. So you have attached a wider dynamic to this certain pixel, a certain range, and you have a geolocation to each pixel. So the idea is actually, with raster you can do fast data processing. It's very simple organized, very simple kind of data sets, and yeah, you have usually, you have actually discrete information to each grid cell assigned. And of course, the smaller the grid cells are, the more higher is the resolution. But as a drawback, you have a problem between discrete and continuous values. For instance, if this here would represent a road, so where's actually the road? Actually, the road won't go like this, for instance. Or if this is a certain kind of land use area, how are actually the borders defined? And this is problematic. This cannot be done really well. You can run local, focal, zonal, and global functions for queries on that point. And you can very easily find out how to transfer certain areas that you have and run algorithm on it to, for instance, to flood. For instance, if this was a water area, you can try, if you have certain thresholds for the green values, you can try to flood it. That could mean if you combine it with an elevation map, for instance, and you can make operations on that you can calculate the likelihood of flooding scenarios very, very easily. You don't have any further knowledge about that, how are the actual streaming or what will happen flooding first, but you can calculate at least the potential very easily without doing any kind of physical calculation. It's even quite precise. Yeah. Then, of course, you can extract certain data. For instance, you want from the elevation map only the middle parts where you don't have too much slopes. It's actually kind of flat, but not in the water. You can use such kind of high and low pass filtering, and then you can find out quite easily where are the next potentials to actually build something or to renovate something, or where are the most critical ones. If you're planning something for Holland, Netherlands, for instance, or something in emerging countries like the city of Bangalore, for instance, where they need always to calculate where actually not to get in the problem. So, yeah, and this picture, for instance, just translated into vector graphics would be something like this. Could be differently because there's certain kind of unconsciousness about the information here. So as vector data, the space is continuous, not broken up in a discrete grid, and we really have like areas which are paired to each other. And maybe I should tell you that maybe like vector was really problematic until maybe the last 5-8 years, because until then the computing power was too slow, even for this kind of 2D information in a large environment was really critical to not work with raster data. So everything was actually based on raster information, and just in the last half decade, it was more transferred to very, very accurate and very, very nice vector information. So what are the typical objects that we use in a GIS system? It's really basic, but it's important that you would have seen it. Points, lines, and shapes, where shapes are polygons, and so on. I think the definition is quite clear, but everything is connected to a GIS information coordinate. So this is important here. In the raster data model, the cell value is the attribute. So the brightness can reflect about how high is the elevation, for instance. And for vector data, the attribute records are linked to point, line, and polygon features. So you have per each coordinate, you have like a vector of single entry points of attributes. Actually a matrix, because you have always a description for this table. Each little point has a table on certain kind of data. So the advantage of rasters, as I said, it's easy to perform logical and math operations. You have a relatively low effort on data acquisition. You can use a satellite, make a scanning. You can use old maps, just scan, done. And yeah, better represents continuous data type data. And vector, this is the old argument, compact data storage requirements. Actually, it's not so true. If you have a high resolution vector data with all kind of curves inside, because usually in the GIS system you don't have arcs, you have single lines, so no Bezier curves and so on. Actually, if you have a high precision there, and you model everything from cadastral data and so on, that's not so much true. So, yes. But relatively to raster information, the same amount of information, it could be a bit more compact. Yes, you can associate unlimited numbers of attributes with specific features. Specific features is, for instance, number of households per address. For instance, address could be like a parcel. You have it connected, income, energy use, everything you can just attach. And what is very fantastic is for planning, because you can do different kind of analysis there. You have a precise geometry and topology of individual data. And that's very nice, because you can make a query, for instance, for all of the city, what are the areas with the oldest buildings in terms of renovation potentials, which have the weakest energy efficiency, for instance, for next urban renovation phase, so you can make kind of very efficiently an analysis. So, as I said, we have those coordinates in GIS systems. The only problem is that the Earth is not just a sphere, it's a geoid. That makes life very complicated. Usually, you don't experience that if you're working with architectural plans. The site is just too small, but everywhere you have actually the bending of the Earth's surface, and that actually shifts everything a little bit. Even on a city scale like Zurich, you have already like kind of effects on there. And if you want to make precise calculations and so on, you get always like the problem. If you don't really recognize that problem, you have shifted angles, messed up areas, because different areas are reported than the real ones in the real world. So you need to use latest at this point a geo-information system, because it's a system which can handle it actually. So geographic coordinate systems use ellipsoids. That means that you try to make little kind of sections into the Earth space and just find out where is the minimal space where it makes sense to have a map drawn with almost no angular and distance distortions. And therefore, you have different kind of ellipsoids for different parts of the world. This information is kind of important for you. If you're working with City Engine, for instance, and you import geodata, it will ask you for a lot of parameters, what kind of projection method, what kind of ellipsoid, and so on. And if you don't put it right there, you just get screwed. You have very funny, nasty distortions, and maybe it could look like for VJ visual, but not for planning actually. So, but it happens really about this projection technology here. And therefore, you have to select a coordinate system that will fit your location and is right on the reference ellipsoid that you have there in that place. Usually, if you go to all the agencies, authorities, they will tell you what is the actual standard of the different kind of parameters. It's kind of a lot of parameters. And if you cannot do that, you just leave away the coordinate system, but you have some problems with the later on queries. So this should be regarded. And so the idea is with the projected coordinate system, you make a transformation from the 3D, actually surface of the Earth, to a 2D space. And the results are distorted shapes, areas, distances, directions, all but shifted. And of course, different kind of projection systems result in different kind of distortions. Here are represented a selection of the most common ones. One of the very easiest is the conic projection, the cylindrical projection. The most common used one is the Mercator. Here, this is this one. And the transverse Mercator projection. Okay, so actually none of them are perfect. The interesting thing is where you don't need to have a kind of fear, because you're using a GIS system, you have always like in the background working this transforming system of the coordinate systems as an algorithm working. And if you make a query on this map here, on this space here, the area size will be always the same, even if the figure is totally different, like if the shifted angles and so on. And this is rather for view ergonomics, and this is more for angular preciseness. So maybe to just explain shortly here, the idea is with the conic projection is that along this tangent that you have here, at this point you get a line around the latitude of the Earth. And along this line, you have all distances and lines are almost precisely drawn. So all the distances are correct. But all the angles are a bit shifted. But around this place here, no problem. But then you have like a certain kind of points where you can do that. For instance, if you make this cut here, you have like, this are very two precise lines, and here will shift away, and here will totally false. So you need to find another interval to be more precise. So you have to do several kind of conic projections there. So the next thing is the cylindric projection. Is actually the same issue. And I think, yeah, the angles are a little bit more correct, since all the information here is just projected on that cylinder. And there the angles stay intact, but in this case, of course, the length is not changing, and that's different. So if you have this projected surface from the cylinder, you can pretty much good understand that you just have to unwrap it, and then you have a plane, you have a 2D description. With the Mercator, there are some more steps involved, but basically the idea is that you really have a rectangular grid, which is easy to operate on, to query on, and so on. And with the transverse Mercator, the idea is not that you have a cylinder, what was with the Mercator, but that you have the possibility for each area where you want to have almost precise surfaces, that you just have a tangent plane placed there, and then you have that projections put there. And this leads to that you usually have a lot of different kind of stripes put together to recreate a map of Switzerland or of Germany or whatever in Europe, for instance. So you really have to compose several ones together. So this all sounds to be very complicated, and I don't want to fear you because this GIS system is doing that automatically for you. And but therefore you will see there are some things that are important that is the system is to be used. Okay. So what are the basic functionalities besides this coordinate issue? Data assembly, the creation of the data set, you have a data storage, that you can run spatial data analysis, and you can do manipulation, and of course you have output hopefully in the end. The assembly and the creation of data is actually kind of straightforward. So you have different kind of data sources. You have a computer in the middle, which gathers all the data. For instance, you have a remote scanning image from a satellite acquired. So there you have already kind of precise ideas. There's a coordinate. What is the resolution? Usually the resolution is depending on which kind of satellite it is. Right now it's between like 50 meters, but the usual scanning resolutions are between 1 to 2 kilometers for instance, for weather data. Then you have a GPS system. You all know that. All your handhelds, mobiles have that inside. And you can track for more precise single-use GPS, for instance. Data passes along your city, and then you can upload it to open source portal for GPS mapping. And then you can create a map with crowdsourced with all different kind of people gathering on different parts on the world, different kind of tracks, buildings, and so on. So this is kind of interesting. Yes, then just manual digitizing and scanning, which is the most painful job. And of course, just data transfer from other databases and the old beloved keyboard, of course. So, and if you all put everything together, then maybe you get a map. In this case, it's a map from Altstetten, and you have thousands of layers inside, in this case, for different kind of land coverages here, and we will have a more precise look afterwards in the exercise on that. The idea is that you have in the GIS this here, you have this map, and in the GIS you have like this map, it's a data representation. Everything outside source information is the so-called universe polygon. And everything inside, for instance here, this is a parcel with the number 3, whatever, or just a zone, and there goes a path into the zone. Yeah, you have the entry in a table. This is a different view. This is a geometric view. This is a table view. You have 2 views in the GIS system. And here is stored the attribute data. So ID 3 has an information of A-4, and in this case, zip code. Right, 22 looks like Germany, for instance. So, and then next example is partial data analysis and manipulation. Which is very common, very easy, is just to reformat the values. Different kind of entries, you just delete entries that you don't need, and then, or you add something new, or you do something with the projection. But very common analysis, what you can do here is, for instance, you create buffers, you have areas. For instance, you have an area today, which is like called Neuerfoltern, and Neuerfoltern, for instance, is likely to be extended in the next year, so you can use a certain kind of buffer function that something is added to this surface. Of course, you can make queries, partial queries. Is there an overlay between area A and area 2? For instance, if I want to build up a new highway, is it passing something like a nature reservoir, for instance? And so I can query it, which will be the best path to don't get problems with different kind of activists. And you can do network analysis. For instance, you have a network graph, and on that network graph you can make queries where most likely congestion for traffic jams and so on, and then you can extend the capacity of the network or distribute it better. Okay. So what you can do as well is you can make reports on that, all of that information. You can select an area here in ArcGIS, And then you can just create an Excel, for instance, what's all inside, what are all the IDs, what is about those buildings, and so on. So we have a little exercise on that, which we will do later on, and you get the feeling. Today it's not the aim that you have big homework. Actually, it's more the aim that we try to solve it within the class and to get a small experience what is a GIS. It's not meant to be that you are the GIS expert in the end, but at least you get a certain kind of feeling. So speaking of GIS systems, doesn't make sense if you don't know where to get data. So that's a big problem in architecture. Usually you have teaching a system, and luckily he will hand over a CD, but mostly sometimes it just happens you get a map, you need to scan it, and you have to draw everything yourself. And in that cases, there are different kind of data sources. I guess most of them you already know. I think everybody knows Google. Google is, what is not known so much is actually Google is not just for you routing and checking out some things. It has a professional component for companies where you can book online routing systems and so on for all logistics and so on. This is very interesting. So from that perspective, Bing Maps has very new visualization techniques. They calculate from different kind of satellite images, almost 3D imagery of this view angles, which can be very interesting for architects for site analysis without actually using 3D model data. If you're luckily, you have in most areas in Europe, you have almost accurate, mostly recent satellite imagery, where you can get a good glimpse of what's actually happened in your urban quarter with this isometric bird eye satellite data. Then OpenStreetMap. You should really check this out. If you don't get any kind of access to certain areas where you need to make a project, it's an open source project, OpenStreetMap, where you can go there to the site. It's almost operating like Google Maps. You're checking out the site, you draw a rectangle, and then you click here, there's a button, Export, and then you can export it to OpenStreetMap format, which can be read by City Engine, for instance, or by ArcMap, the GIS front end. It's not readable by CAD software, because all this kind of coordinate system transformation is not working. Usually what you get out of this kind of mapping data here are surfaces for different kind of land uses available. Sometimes you have building footprints, like here in Zurich. It's a very nice coverage, actually, of data. And you get all bicycle paths, you get highway paths, so you can do a lot of different kind of analysis and queries. And if you make a site analysis, you get a lot of information what the others won't have, actually, just from using this open source one. And interestingly, it's used almost covered the whole world. So, but you need to know this is a public effort, so some pieces of data may be imprecise. So you should always compare with other available sources if it may be right. As long as you are studying here at ETH, there's a portal called GeoVite. And with GeoVite, sometimes you need to try out if your student account is working already. Sometimes you need an assistant to ask for permissions that you can download the data. But with GeoVite, you get all the Swiss topo information just for free. You just need to go to your area, first make a marker here, then you select here, oh, what do I want to have? Oh, maybe elevation map. Not just the pixel data, maybe just the DXF, because it's better for Rhino for prototyping and so on. You can just select it, press download, and you have a shopping cart, and then you have really the truncated file for that area. And if you do it more and more iterations, you get the vector 25, vector 200, even old thematic maps of Zurich, like 100 years ago, what Zurich looking like. If you're making some site analysis for your design studios, I think it's a very valuable tool, at least if it's in Switzerland. For all the data in Switzerland, you have a good coverage. So it's only Swiss. And for Zurich, of course, Zurich Plan, the revised GIS front end of Zürichplan. You have all the kind of Bebauungszone and Zonenplan and so on covered, and nature reservate. You can go there, check it out, and get the information. It's really nice. So, and usually you can use it just straight away, but with this one and this one, you need to have a GIS-capable tool, or at least a tool which is capable to read GIS data. Okay. So maybe GIS and urban planning, what you can actually do with it. You can make, as I said, a spatial analysis. To understand spatial interdependencies. And you can create thematic maps, which is just focus on a certain information, like unemployment rate or maybe sun hours. Maybe that's better. Maybe in combination, it's nice as well. And geocommunication. You can actually communicate. The one thing is the information that you queried. The other thing is how you lay out the design so that somebody will read the map, understand the map. I think architects do already a very nice job. And this is wrong, not geocommunication, geoservices. This is, of course, value-added services that you can do from that kind of information. Okay. So maybe some examples here. So those two images are representing actually the same information. So what is different? It's about population size here. In the first image, there are little tiny squares connected to each kind of building inside this area here in Vienna. So this is a bit problematic since there is always a kind of little change in the building structure. So querying kind of statistical insights is problematic, but what you can see nicely here is, of course, the building structure connected with population size. So that's sometimes gives a lot of insights here. And then, where you don't have any kind of insights, but you can better evaluate it for statistics, is the querying of population size per pixel grid. So you just lay over a grid, and then you draw this kind of little blocks. So this needs to be understood that not for every kind of analysis, certain kind of images are the best. You need always to find out what are the best things here, what could be used. For geocommunication, for instance, it's very common. Like a black plan here, you have all the buildings are put in red, and everything else is a bit formatted, a bit pastel, so that you can really focus on the buildings, for instance. Or the same with the green areas. Or even here with all the traffic infrastructure, everything is made in black in that case. But the Donau is actually as well a nice traffic, but okay. So for instance, if you make a query on whole Vienna, what is the different kind of building heights, you get such kind of map that you can very easily see that the higher density, the higher buildings are actually placed somehow in the middle, in the center, and then it goes like very greenish, which is almost lower than 9 meters, so almost like just 1 to 2 story housing. Then other examples what you can make are like Akademikerquote, so how many people are actually here with a higher education degree, how are they spread through the city. That's very important for segregation, different kind of things, if you want to circumvent that. And if you bring this maybe into relation with the numbers of persons with the migrants, then it is very interesting as well. Maybe there are certain kind of trends where you need to check out for better integration, and as well if you see what are like the best categories for living. So for instance, category A in Vienna is highest standard housing, and then you have even lowest standard housing, and you can really compare then different kind of sheets together. And this helps a lot if you just going into a certain area and you want to make a development proposal, and you have this data actually available in most cities from statistics and planning. So then you can really see what is actually the fingerprint of your little tiny block, like Altstädt in this case, here in Zurich for you, and find out about this. Okay, so this would have been the first part of the lecture. Now you have a feeling with a lot of maps. You can do a lot of impressive slides. And now are the next impressive slides.